Sophie McCabe, and today I will be presenting on my findings from Lab 4. In my presentation, I will have 3 sections. The first is an introduction, where I will discuss the purpose of the lab, the fundamental principles involved, and a summary of my results. Second, I will be discussing my data, measurements, and observations in my experiment on the circuit simulator. Finally, I will be concluding my presentation with my answers to a few thought-provoking questions. The purpose of this lab is to apply the knowledge of circuits that we have developed in our lectures to predict various changes in potential difference in conventional current caused by various types of circuit setups, and to further examine the time dependence of the capacitors and how they impact a circuit. In order to accomplish this, we used a few fundamental principles. The first is the Kirkhof loop rule, which states that the total voltage drop across an entire loop of a circuit is 0. This is due to the EMF supplying voltage and the resistor slowly consuming it to make the net change in voltage 0. The next fundamental principle that we used is the node rule, which states that the current coming into and out of each junction is the same because the current is a constant conserved throughout the entire circuit. This is particularly useful in calculating current resulting from junctions with resistors in parallel where the current may not be split evenly. The last main principle in this lab is the time dependence of capacitors. A brief summary of my results is that the stronger a resistor is, the more voltage drop it has. Capacitors create a time dependency in circuits, and my RC value for my final circuit was 0.02 seconds off from the simulation prediction. In my first part of the lab, I worked with the series circuit, consisting of 2 batteries, each 1.5 volts, and 2 resistors. The first one 47 ohms and the second 100 ohms. In order to predict the currents of I1 and I2, I first came to the conclusion that since there are no junctions, I1 has to equal I2 since the currents are equal. I then simplified the resistors in the series to one resistor with the sum of the resistance, and then used the Kirkhof loop rule to solve for the current, which I found to be 0.0204 amperes. When I used the PhET lab to check, I found that this to be the accurate reading for both I1 and I2, meaning that my prediction was correct. When I reversed the connections of one of the ammeters, I found that the current reading was to be the same. I then replaced one of the ammeters with a voltmeter, creating an open circuit where there could not be a current flow. The ammeter read 0 amps, indicating no current flow due to the openness of the circuit, and the voltmeter read 3 volts across the break in the circuit. This voltage makes sense because the broken circuit does not allow for the electrons to flow, creating voltage drop that matches the EMF. After removing the voltmeter and closing the circuit, I used a voltmeter to measure each of the voltage drops across the different parts of the circuit, shown here. Since the circuit has no junctions, I used the fact that the current is constant to calculate the resistances along each of these portions of the circuit using the definition of resistance, voltage drop divided by current. Based on the Kirkhof loop rule, the summation of the voltage across the entire circuit should be 0 volts, but it ended up being negative 0.01 volts, which is probably a slight discrepancy of numbers and results from the current not being 100% accurate in real life or some rounding error. In the graph of the electric potential, I showed the voltage decreasing along the resistors and kept the relative drops consistent with how strong each of the resistors were and the 0 voltage drops across the wires, which I found earlier in the lab. There is no ammeter change in reading when you add a voltmeter, because there is no change in the current flow through the ammeter. The current across the 100 ohm resistor stayed constant when the circuit is still in series, but when it went into parallel, the current flow changed, since it could follow the path of least resistance by avoiding the circuit resistor and flowing through the ammeter. For the second part of the lab, I made a new circuit with a capacitor. Initially, I set up a circuit with a 9-volt battery, a 10 ohm bulb, and a 200 millifarad capacitor. When I connected the circuit, the light starts out bright and then dims as the capacitor begins to charge, and the current flow decreases until it stops. The same thing happened when the battery is replaced by just the capacitor as it discharges. When using the 10 ohm bulb, it took the capacitor 6.75 seconds to charge and 8.94 seconds to discharge. When using the 20 ohm bulb, it took the capacitor 8.82 seconds to charge and 18.48 seconds to discharge. For the last part of this lab, I calculated the RC value for the circuit shown on the screen using the voltage drop data. I set up a linear regression of the data that I took during the lab and then calculated the slope as a reciprocal of the RC value, which I found to be 6.02 seconds. This ended up being slightly above the one from the circuit value, which was 6 seconds. Before I conclude, I would like to address two key questions. First, if I was doing this in real life, the ammeter would have some internal resistance, which would cause a voltage drop across the ammeter, decreasing the voltage drops across the other resistors in order to follow the Kirkhof loop rule. Second, if I were to be using a real battery and a real capacitor with no resistor, in real life the capacitor would take longer to charge than in the simulation because it would have the battery would have some internal resistance. Thank you for watching, and I look forward to discussing more physics content during Lab 5.